Hello everyone, welcome to Unit 4, Lesson 5, Notes for Connect the Dots on page 2. By the end of this, you should be able to answer the guiding question, how are Lewis dot diagrams used to model the bonding of covalent molecules? Lunchtime, not really. The activity uses puzzle shapes. I will try and post the puzzle piece document online. Please email me if you can't find it. Okay, notes. The general rule for drawing simple Lewis structures that contain hydrogen, oxygen, and carbon is called the honk 1, 2, 3, 4 rule, where hydrogen forms one bond, great. Oxygen forms 2 bonds, nitrogen forms 3 bonds, and carbon forms 4. These are all based on how many unpaired electrons there are when we draw their Lewis dot diagrams. Okay, so for nitrogen, we know it has how many valence electrons?
3.
No. Nitrogen has 5 because it is in group 5A. So we draw its Lewis dot diagram as such. You always start by writing them single before you pair them up. Just like when we did orbital diagrams, electrons go single before you pair them up. Okay? And it's always 4 spots because they can always form up to 4 bonds. So carbon with 4 valence electrons, you draw it as 1, 2, 3, 4. So the honk 1, 2, 3, 4 rule indicates how many unpaired electrons there are and lets us know how many bonds they need to form. Okay? So these are our Lewis dot diagrams, and there were some examples. We can do some more. So for example, we also have chlorine that has how many valence electrons? 7 valence electrons. So when we draw its Lewis dot diagram, we start single. 1, 2, 3, 4, 5, 6, 7. Okay, so how many bonds would we expect chlorine to form? 1 bond, because there is 1 unpaired electron. So 1 bond for 1 unpaired electron. Now, with anything in chemistry, there are exceptions. We do not cover exceptions in this class. Okay? If you want that torture and that joy, take AP Chemistry. What if we had xenon? How many valence electrons does xenon have? 8. So 1, 2, 3, 4, 5, 6, 7, 8. What's the most number of electrons you could have in a Lewis dot diagram? 8. Okay. So this idea of going to 8, we're going to touch on more in the next set of notes, but this is our octet rule. That elements will form bonds in order to have 8 around them. Can you think of one that might be an exception to that rule, though? Hydrogen. That is the most obvious one. Cool. So Lewis dot structures are diagrams that show how valence electrons are arranged in a molecule. We can also use these Lewis dot structures to draw structural formulas. Any electrons that are shared between 2 nonmetals form a bond that we represent as a line. and any electrons that are not shared remain as dots called lone pairs. All the electrons are still going to be there, you just change how you represent bonds. The dots become lines for bonds. So we're going to look at some examples. Ready? Okay, so first example, water, because, hey, why not? Oxygen has how many valence electrons? So we draw 1, 2, 3, 4, 5, 6. Hydrogen has how many valence electrons? So if this is hydrogen, where are we most likely to put it? The bottom and the left, right? We're going to pair them up. So that hydrogen is technically all paired up. It just does a duet instead of an octet. It's not that musically talented. And then oxygen has its octet. It has all 8 around it. Okay? If we were then to draw our structural formula, we change the bonds to lines. But everything else stays the same. So that is our structural formula. So Lewis dot diagram, and then here is our structural formula. Was anybody confused by the super long, skinny electrons that weren't paired up, but it looked like they were going in a line to go somewhere, right? We were confused. What might those be possibly trying to represent? I talked to one group about it. Triple or double bond, right? So if we looked at carbon dioxide, carbon has how many valence electrons? 4. So 1, 2, 3, 4, and then oxygen has how many? 6. So how many unpaired? 2, right? So I'm going to start by pairing oxygen with one of carbons. So there's 3, 4, 5, 6. And then I'll pair my other oxygen up so it's started. Are all of them paired up though? No, so I can actually take this oxygen and pair up one more time with that carbon and do the same thing on both sides. So I'm going to move my oxygen electrons. So I still have 6 red electrons from oxygen. And then I can move carbons in so that it is still pairing up and they're all paired up. Right? They all have a buddy. Does carbon still have now 8 around it? Right? Through all of its sharing, it has 8. Do the oxygens? Yeah. 4 that are shared. Ooh, it's like a Venn diagram, what they have in common. It's in the middle. And then what's only theirs is not shared. So if we were to take this and draw, and I'm writing that super small, draw the structural formula, overcompensate and draw it super huge. How many lines would I draw between the carbon and one oxygen? 2. Double bond. And then we keep the lone pair electrons that were sitting on oxygen. That makes sense? Can you see why you might want to use a whiteboard? Or why highlighters or colored pencils might be useful if you're into color? Now, if you're not into color, how could you possibly differentiate between your electrons if you're pairing them up? Open circle and closed circle. Thank you. And in case people who are listening are wondering, we are live from period 4. So while I transition and end these, please answer the guiding question at the bottom of page 2. And thank you for tuning in and participating.